So starting with Theo Abadilla. Are you ready, Theo?
Okay, hi everyone. My name is Theo Abadilla. I'll be a senior this coming fall at Crescent Valley High School in Corvallis, Oregon. And today I'll be sharing about my research project that I did at HP Corvallis over the summer. Here's a picture of me at my working station. And so my research project was a build off of a initial concept and initial testing done by Dave Welter, who's an engineer at HP, and he was taking a look at some different PTFE vent membranes. The vent membranes are used to separate liquid and air. They're essentially just layered synthetics that create millions of pores that are large enough to let air molecules through, but too small to let water droplets or liquids through. And my research was done to better understand the characteristics and features of each vent so that the engineers at HP could better understand how to apply them in different projects, and as well as test the variation within the products themselves, because HP purchases them from an outside company, and we wanted to check the consistency and reliability of each vent. And here's a picture of a kind of zoomed in look at the vents, and you can see the pores here. And then this is just a picture of the vents attached to the testing parts itself. So for the setup, for the test, it was again building off of Dave's initial setup where he had one transducer and one syringe clone pump. And the transducers that we decided to use are Model 38 transducers, which is just kind of sets the restrictions for where we can collect data. And the transducers are essentially just pressure sensors that can read the pressure from the clone pumps and then send a signal to the computer, which stores the data. So we multiplied David's setup out by 4 so that we could have just more efficient data collection. So we used 4 separate transducers paired with 4 separate clone pumps, and we ran a calibration of all of the transducers using this calibrated pressure manometer and pressure generator, which kind of just sets the standard and helps zero our transducers to make sure we have accurate and precise results in our testing. And once we were all happy with our setup, we had to verify to make sure that our setup was yielding accurate results. So we ran a complete gauge R&R, which is testing the reproducibility and the repeatability of our test. The test itself breaks down our workstation into its variables to see any discrepancies among the testing. So here's a little table that shows our operators. So whoever's running the experiment, if there's any discrepancies on who's actually manning the stations, and see if there's any differences between us. And then the stations itself, since we had 4 different transducers and 4 different pumps, we wanted to make sure they were all yielding similar results. And to do this, we ran a series of tests. We had 8 different parts with 3 different operators on 4 stations, and we ran each part 4 times for a total of 128 tests per person, but we did have 4 stations, so it was a little bit more efficient. And from this, we inputted all of our data into Jump9, which is a program that HP uses to test different things. And we got our PT, which is the precision to tolerance ratio, and the kind of standard and threshold that we needed to get was under a 30%. And we ended up getting a 3.74%, which is super good. So we were super satisfied with that. And we got it all checked off with Dave, and we started to build our actual parts for testing. So the parts itself, these are what we were testing on our stations, and we had to build each part and we were testing the vent membranes itself, and they were attached to a barrel cap, which is just so that we had a simple test interface that we didn't have to machine. We already had the parts for, and then we plugged in these labyrinth plugs that go right here, and they're just friction fitted in, and they fit snugly and create a nice seal so that no air can leak through there. And then there's an adhesive on the back of the vents that went right onto here and onto the labyrinth plug. And then we needed a way to attach this interface to the stations itself. So we used 2-part epoxy to adhere a lure screw-on fitting, which is just a little plastic piece here that screws onto the tubes that are attached to the transducers and clone pumps. And so we had to build 36 of these parts total. We had 9 different categories of vents. So each vent has different configurations, and then we had 4 parts per category, so that's 36 total. And since we did have 4 stations and they were all yielded really similar results and really accurate results, we were able to test 4 at a time. So the testing process itself, here's an example from Dave's initial testing. This is a graph. He used some different flow rates than we did, but it's the same concept. You pull on the clone pumps at different flow rates to get this kind of constant rate. Each one of these lines represents a part. These are all different parts, but ours were all the same on the graphs, which I'll show you in a sec. But so on the graphs, each one of these bumps are just a different pull flow rate. And we took the averages around this flat area because we didn't want data from when the stations were working and when it was dynamic. We wanted the more precise averages here. And we had 4 different points of data because we pulled at 4 different flow rates. So we were able to create a line of best fit that went through all of the points. And so we could use that to predict how the vents would perform in future pressures. So we chose 5, 13, 18, and 23 cc's per minute because that's just the restrictions we had on our clone pumps, and we wanted a tighter sample size right here. We didn't want anything too spread out. Like in Dave's, he went up to 50 cc's per minute, and we decided that was a little unnecessary. So we just kept it within the 5 to 25 range. And here are a few examples of the results. So we actually had to run the test twice because we ran into some issues. So this is the first kind of example of the first test. This is an example from reel 4. So each one of these parts should have had the same vents. So they should have performed very similar. And as you can see, the gray one, this was attached to channel 1, performed about normally compared to some of the data that we got from the gauge R&R and then the initial testing. But these 3 lines down here seemed way closer to 0 than all of the other ones. So that kind of led us to believe there was probably an issue with the parts because we verified that our station was all set up correctly. So we kind of assumed that there's probably a leak somewhere between the epoxy joint and the plastic part itself. So we went through and globbed over with more epoxy to try to seal any leaks that might be happening. And we ran the tests again and with the same exact parts. And you can see there's some improvements here. The yellow and the gray are very similar, but the green one yielded a little bit of a weirder result where it was a lot deeper than the others. And then this blue one was still kind of struggling. So there's probably a leak on this one still. And unfortunately, this testing happened on the last day I was able to be on campus. So I wasn't able to finish, but some next steps, since I do have an extension on my internship, I probably will have 1 more week still. So that allows me to hopefully return to campus and run some simple leak tests on the parts to make sure that is the problem that we're having. And I think this is probably the key thing we need to do. So if we can determine that there are leaks in some of our parts, then we can probably create a new batch of parts with a better system of attaching the lure locks to the parts itself, and then retry the testing. So that kind of covers everything that I did during my project. So some things I've learned is I learned how to verify a testing setup during the Gauge R&R. It was a super great experience to run. We built a test in SuperSequence, which is another program that HP uses that works with the clone pumps. That's when you pull at different flow rates. And then analyzing and presenting data. Some Excel skills. Since all the data is stored in Excel skills, I got to graph them all and then find averages and then find a line of best fit through those averages. I got to work with transducers, which was super awesome. They're such powerful and precise devices, but they are super finicky and sensitive. So working with that was such an awesome and interesting experience. And then I'd say the biggest lesson I've learned so far from this was that testing never really works perfectly the first time you do it. You always have to analyze your results. And if it's not what you think should be representing your test, then you check your variables again and see if there's anything you can do to improve your testing. And some huge thank yous. Brian Easton was my mentor at HP. He was super awesome and helped me through every step of being an intern. Bill Learn was my manager at HP. He was super welcoming and very understanding and super helpful. Dave Welter was the head engineer that introduced this project to us. So I had to thank him a ton for helping us through this process. Kristen Gore assisted us during the Gauge R&R, and she showed us how everything worked and helped us plug everything into Jump 9. Joe Lara was also in our group, and he helps us be our third operator. So he was in our Gauge R&R, the third person in the operator variable. And then of course, Jennifer Henry was our awesome teacher monitor. Thank you so much for helping us through the process of being interns. And then of course, Saturday Academy for giving us such an awesome opportunity. And now, questions.
Great work, Theo. Now's your chance to ask some questions in the Zoom chat. And let's give Theo a chance to keep talking about what he did. Some awesome work. All right, we've got some questions. What do you think was the hardest part of your internship?
I actually broke my leg like halfway through my internship. So I was out for about a week and we had to like have a pause. It was right during the Gauge R&R. So it took a week and then I got to get back and was in the office on crutches. So that was probably the biggest challenge, but it was super fun. Brian and Bill were super helpful and they let me work from home for a bit. So I'd say that was probably the biggest issue I ran into, but then on a more project-based hardships, just during the testing part, trying to find what went wrong and see how I can improve is probably the biggest thing that we had to get through.
All right, another question. What was your biggest learning experience of the project?
I'd say the biggest learning experience was probably just learning to get through testing again. Just nothing works well the first time. You have to learn from every test you do, and that can be applied in so many things in life, especially in engineering. Just problem solving, working through the hardships, and then finding your next steps.
Has this internship changed your college or after college plans?
I think not exactly changed, but it's kind of reassured me that I do want to go into an engineering type of thing. The internship has been very hands-on, and early on I got to do a lot of hands-on work. So that kind of sparked more of an interest in the mechanical engineering side. So possibly that.
All right, and last question, what sort of technology might take advantage of this research?
Oh, right. So the vents are often used in the industry during thermal inkjet, which is printing stuff. And then there's been a few medical applications. I can't really talk about the actual projects that HP will be using because they haven't been released yet, but they have some pretty cool stuff in the future.
Awesome. Thank you.
Yeah, thank you guys.
Great work.
Thanks.
Okay, next up we have Simone.
Hello, give me one sec. Can you see my screen okay?
Yes.
Okay. All right. Hello, everybody. My name is Simone Moulton. I'm going into my senior year at Crescent Valley High School, and my summer internship was at the HP Corvallis site. Today, I'll be sharing with you my main summer project. So when in doubt, burn it. Let's talk lessons in cutting waste and optimizing yield from HP. To give us some background, let's start with the background, problem, and objective of this project. HP's page-wide printer, which is shown in Figure 1, dispenses ink in a single sweep by a print head that spans the entire width of the page. Essentially, this means that a page of print can be delivered in one go. Uses page-wide technology, various stationary print heads that span the width of the page with thousands of ink nozzles to dispense ink onto the paper. It's built to be fast with up to 75 pages dispensed per minute, and it's built to be reliable. Oh, sorry. There we go. The print bar shown in Figure 2 is the component of the printer that dispenses the ink onto the paper. There are three main components of the print bar. There's the UMA, or the upper manifold assembly, shown in the dusty blue color, the middle manifold assembly, shown in the gray, and the lower manifold assembly, shown in the yellow. Today, we'll be focused on the upper manifold assembly. The upper manifold assembly, or the UMA, is the upper part of the print bar. It consists of two plates and one frame, which are shown in Figures 2, 3, and 4 as separate components. When welded together with a plate on each side of the frame, as shown in Figure 5 and Figure 6, the UMA holds fluidic channels that serve as ink pathways. The part is welded by a laser welding and consists of two types of weld: fluidic welds, which are welds that contain fluid, such as ink, and support welds, which provide support to the structure of the UMA. Overheating from the laser during the welding process can cause bubbling or burns in these welds. So what's the problem? Well, fluidic welds require fully intact welds, so no bubbling, in order to be functional. This prevents leakage between the channels and externally. This has been proven by extensive prior testing. However, the criteria for scrapping incomplete support welds was pretty vague, it was arbitrary, and it wasn't yet supported by data. This resulted in the potentially unnecessary scrapping of parts that contained incomplete support welds. If you turn your attention to Figure 7 and Figure 8, you'll see circled some examples of incomplete welds and bad welds. They are characterized by their lighter color, which is evidence of bubbling. Our objective was to create guidelines on what to scrap and what not to scrap when we see an incomplete support weld. Figure 8 shows the boot plate support welds and the upper plate support welds highlighted in red. These are the welds we're focusing on. So let's talk key concepts and experimental design. Here's some cause and effect thought process that went into why we decided to purposefully burn our welds. Incomplete support welds are welds that display bubbling. We need to recreate incomplete welds, which means we need to put bubbles into welds. That means we need to manufacture bubbles, which means we need to burn the plastic welds. These incomplete welds, or these burned welds, were to be purposefully manufactured by adjusting the laser welder's speed to execute specific degrees and placement of bubbles and burns. The laser welder is shown in Figure 11. If you look to Figures 9 and 10, you'll see the laser speed map for the boot plate and the upper plates. Each color corresponds with the laser speed. The higher the laser speed, the less the area is heated within a time frame. The map was created via trial and error testing, and consistently burned areas had to have their laser speed increased in order to compensate. The fastest speed shown is in orange at 2,700 millimeters per second. So we knew that once we manufactured our purposefully incomplete welds, support welds, we would need a consistent criteria to test them on. So enter our core 3 tests: the leak test, the XYZ test, and the push test. The leak test tests the rate of air leakage from fluidic channels to ensure that it's within acceptable bounds. The XYZ test makes sure that all dimensions of a part are within acceptable bounds. It measures the boot and upper plate for planarity. And the push test tests the tensile strength by pushing downwards on the plate in question. It can be used to test how much pressure it takes to separate plates. So how did we design our incomplete welds? Well, we created 5 different variations in order to test different points of interest. Variation 1 was burning all boot plate support welds. They were burned enough to produce a high volume of bubbles, but not enough to produce significant outgassing. Outgassing is the process where the UMA's plastic material is exposed to heat and releases a gas that condenses and often renders the part unusable. Variation 2, we burned all boot plate straights. These were chosen for their frequency and their dissymmetry across the plate to observe how unbalanced burns would affect planarity. Variation 3, we burned all boot plate circulars. These were chosen for their unique shape. Isolated burning could offer insight into how circular supports corresponded with part integrity. Variation 4, we burned all boot plate orange. The orange were all areas that were heated to 2,700 as shown on our previous laser map, or the former problem burn sites. So we wanted to see, well, what happens if we do let them burn? And variation 5 was the upper plate bottom weld. This was another former problem burn site that had repeatedly been affected by bubbles. Our experimental setup was the 5 variations that you just saw. We tested 3 speeds per variation, 5 parts per speed, and we did the XYZ, leak, and push tests, or 3 tests per part. Our general flowchart was manufacturing of the part, recording the serial number, leak test, recording the results, XYZ test, recording the results, and push test, recording the results. So let's talk about the results. At an initial look, we'll see that 75 parts were tested in total. 63 of these parts passed all 3 tests, and no part that failed more than 1 test. 58% of fails were from leak tests, or the tests that test the channel leak rates. 42% of fails were from the XYZ test, which tests for plate planarity, and 0% of fails were from the push test, which tests tensile strength. 675 data points were collected, and generally the trend we saw was that the more extreme the burns, or the slower the laser speed for welding, the more failures, or the closer to failure. If we continue to take an additional look at the slowest speeds tested for each variation, we'll see that variation 5 fared the best in the push test, but the worst in the leak test. Variation 1 fared the worst in the push test, and variations 1, 2, 3, and 4 all stayed with their averages within the plus minus 0.05 PSI specs for the leak test. The push test was surprising. I certainly did not expect 0% of parts to fail the push test. We did see a general trend where the more intact the weld, or the closer the test weld's proximity was to normal speed, the increased performance, and vice versa. The worse the burn, the worse the performance. However, all parts were over 100 newtons higher or stronger than the minimum accepted push test, which was 400 newtons. That's well within acceptable bounds. And this exaggerated level of burn we're testing compared to the naturally occurring support burns is even more promising for the strength of these parts. The leak test saw something else that was really interesting. 71% of leak test failure occurred in variation 5 at a speed of 1200 millimeters per second, which was the slowest speed that variation 5 was subjected to. The acceptable range is within plus minus 0.05 PSI for the leak test. However, 3/4 of the channel's averages were outside of this acceptable leak range if you look at figure 16. But why is that? Well, variation 5's burned weld displayed significant outgassing at 1200 millimeters per second. And variation 5's weld was directly opposite to all 4 channels that are tested in the leak test. And we saw that the outgassing migrated all the way to the opposite side, likely into the fluidic channels. This is a sign that the welds were burnt enough to potentially affect boot plate fluidic channels. If you look to figure 20, you'll see the front-back positioning. It's not quite to scale, but those green rectangles are opposite of one another. If we look further at this leak test, we'll see that variation 5 on the right and variation 2 on the right compared. Variation 2 was burned at a slower speed, so a more extreme burn, and its burns covered more surface area. However, it was well within leak test range compared to variation 5. This indicates that it's not necessarily the speed that these welds were burned at or the amount of surface area they cover, but more so the exact geography of their placement that has a more extreme effect on part integrity. So as a conclusion, the high success rate of the parts is a really promising sign for decreasing scrap and maximizing yield. Manufactured burns were considerably more extreme than any naturally occurring ones, and yet they still largely passed. The likelihood of part failure varies with burn size, placement, and other noticeable characteristics like how much area is this burn taking up? How close is it to a fluidic weld? Is there outgassing, any noticeable collapse in the part, etc.? But our general conclusion is that the average bubbles on a support weld, if even present, prove little to no threat to the functionality or the integrity of the UMA part. While failures do occur, they are happening in the leak and XYZ tests. 100% of parts go through these two tests, so if failure is present, it will be caught. Parts with incomplete support welds are likely still functional and are worth sending down assembly line given they pass both leak and XYZ tests. Looking forward, we would probably rerun experiment to correct for some error. For example, there was error with the leak tests. Rerunning the test to check for false negatives when a test failed was something we were doing at the beginning because false negatives are possible, but false positives aren't. We stopped after realizing that the high pressurization of the leak test could cause particles to be blown into the leaks, essentially clogging them. And this would make each leak test retest artificially better. We'd also add more controls, test more variations and more trials, test actual scrapped parts for real world application, remove fluidic welds and push test support welds, put burn support welds through the whole assembly line. So what did I learn throughout this process? Well, there's no shame in not knowing something, and more often than not, people are really happy to help. Also take advantage of the classes, the seminars, and the interviews that are offered. Always allot time for figuring out a new system and troubleshooting. Mistakes happen, prepare cushion time, be kind to yourself, give breathing room to yourself. Take note of your error, it's going to be really valuable for future experimentation. Set goals for each day, experiment, and project, and go broad and specific with them. I'd like to thank Mark Freeman, Solomon Amiani, John Erickson, Martin Castaneda, Spencer Helterline, Stephen Reinhardt, Jennifer Henry, and I'd really like to thank my mentor, Perrin Mao, for all their incredible help and support throughout this internship. Thank you to HP and ASE. I really appreciate it. This was a super fantastic and valuable experience.
Great work, Simone. Awesome job. Now's your chance for questions in the chat, please. What's one thing you would change with your experiment?
I think that the error that I had that we noticed halfway through was something we kind of ended up changing halfway through. And that kind of messes a little bit with the controls, in all honesty. I think if I was to go back, I would just let whatever the leak test record that. Obviously, false negatives are possible, but it's better to be on the safer side with a false negative than to overinflate your statistics with false positives.
What was your favorite aspect of the internship?
Getting to work in a lab setting was so cool. It's something that I think previously I felt kind of nervous about, but through this experience and getting to interact with engineers and my mentor and other interns, it's just really enforced like how much I really enjoy the hands-on aspects of engineering.
How did you determine what was too much outgassing?
So outgassing happens. We saw it in pretty much every single one of our burns to a certain extent. However, on our first time burning the all support welds, we burned it way too slow. And basically the outgassing clouded up all the chambers within the part, and you couldn't really see anything, and it smelled horrible, and it was coming out the sides, and it was burned plastic everywhere. And so that would not be a part that would be going down the line. And so that was kind of like where we're like, okay, we're not going to get close to that sort of damage because that damage isn't applicable to what our research is trying to find right now.
Do you see any applications for this kind of laser welding that looks promising, either within the field you're working in or at large?
I think laser welding is a really, really awesome tool. And I know HP is heavily utilizing it for the construction of these parts. I think that it's useful to continue to do more research into the parts that are being manufactured via laser welding. So like what we're doing here, we manufacture this with laser welding. We're able to kind of like adjust the levels of burnage and stuff with it. So how do I word this? How does laser welding impact these parts, and how do these kinds of welds impact the integrity of the part?
Very cool. Great work.
Thank you.
Thank you so much, Simone. All right. Aaron Lee, you're up next.
Yeah, for sure. Wait, hold on, let me just find my presentation real quick. Okay. Can y'all see this?
Yep, we're good.
Okay. Super. All right. Hi, I'm Aaron. I'm a rising senior at Sunset High School, so that's in Portland, Oregon. And this summer I was an ACE intern for HP at their Corvallis site. And as you can probably infer from the title, I was primarily working on adjusting a computer vision program so that there would be fewer false negatives. And I'll sort of explain what that means later on. But first, some background about me and this internship. So the field of study of my internship was in control systems engineering. So when I went on site, a lot of the really cool stuff I was exposed to were the clean rooms and final production facility. And control systems engineering has a lot of applications, particularly in production. So what I worked on this internship was like really related to controls engineering, particularly in defect detection. So that has a lot to do with quality control and measuring sort of how like quality control impacts the line yield. And then also though, like the computer vision component of this internship, and as well as some controls engineering, can also be sort of applied to product assembly. So there's a lot of stuff to do with production besides defect detection too. And then right before like I continue any further, just want to say a massive shout out to HP, just because they do a lot of community outreach programs like this partnership with Saturday Academy. So, and this was a phenomenal experience. So I just want to say thank you to HP. So yeah, talking about the beginning of this internship. So I think they had this on a slide earlier, but I kind of look like a mummy, and that's because there's not supposed to be a lot of debris in the final production facility. So basically, it was in this facility that I got a better understanding of my project. So that was where my mentor Tauha gave me a lot of guidance in terms of what my project was, and gave me sort of like requirements to hit. And then from there, I was able to do deliverables and schedule those deliverables in a Gantt chart, so that my manager and Tauha could see, I guess, the plan. And then also one really cool part of entering the final production facility was I was able to understand like more about sort of the role my project played in like how these printer parts are being manufactured. And I sort of like realized that my project was a very, very small portion of it. It's just like pre-inspection for like one of the like 9 product areas, machine areas. So it was really useful in terms of understanding the scale of my project. And that sort of helped me with like sort of like grasping what exactly I was doing. Also earlier on in this internship, I faced like a couple tech difficulties, and they sort of taught me a lot about like, you know, if there's a will, there's a way, right? So even though like some of these tech difficulties can't get resolved overnight, there's always like something else that you can do in the meantime. So for example, when I was having issues with my VPN and network, I spent a lot more of that time like while waiting in queues to get tech support. I spent a lot of time like watching video tutorials and taking notes, so I had a better understanding. So like when they helped me fix some of that, I could like have more knowledge to hit the ground running. And then also when I was struggling with Insight Explorer, which is like the Cognex vision system application I was using to just the computer vision program, I had some issues with that. So then I was able to find workarounds with my mentor Tauha, using a virtual machine. And then, yeah, so earlier I brought up false negatives. So I just wanted to sort of take the time to explain what that means. So basically, as you can see on the right, there's this chart, right? So for example, so there's actual value and predicted value. So what that really means in my internship was I was really measuring whether a part was good or bad. So if the part in actuality was good and the vision system said it was a good part, that's a true positive. If the part was bad and the vision system said it was a bad part, that's a true negative. So that's sort of like what you want. And then, but there's also like a type 1 error, which is a false positive. So that's if the part in actuality is bad, but the vision system says it's a good part. So like you end up shipping the part out anyways, right? So then you have to deal with like product line recalls and stuff like that. So that's a little bit like a lot more hassle. But what I was primarily working on was false negatives. So when the part in actuality was good, but the vision system was saying it was bad, so we were scrapping the parts. So that leads to a lot of waste. So by reducing false negatives, we'd be able to reduce waste. So that's sort of the purpose of my internship. So if you look at this, this was sort of like what the original program, vision system program we had looked like. So as you can see, there's a circle here. So it's just the primary purpose of this program is just to determine like the coordinates of the fiducial. And as you can see, there's like a fiducial for both of these, but it's not recognizing the fiducial on the left because it doesn't have like that circle and the marker and stuff. It's not giving numbers. So like if you look at the primary difference between these two, like it's the contrast. So the vision system was struggling with identifying the fiducial in low contrast images, but it could do it quite well in high contrast images. So from there, like my main purpose, like what I was focusing on was finding a way for making the adjustments so that the new program could handle low contrast images better. Okay, so I did that by optimizing some of the parameters of some of the functions that were already built by HP engineers within the program. So for example, this thing called find patmax patterns, I lowered the contrast threshold just because that's better practice for low contrast images. And then I shrunk the scale tolerance to find the right circle because there was sometimes an issue with the vision system finding the wrong circle when like trying to locate the fiducial. With the point filter, I lowered the binarization threshold to turns grayscale to black and white, so that there would be more white than black. With extract blobs, I lowered the blob threshold to detect blobs with lower contrast. And then with the find circle function, I changed the edge transitions to all become light to dark, from light to dark to light, for better edge polarity. So basically, like all of that was just to make it so that the new program would process low contrast images better. And that's exactly what happens. So after all those changes, you can see on the left that, these are like pretty similar in terms of like the pretty low contrast, but the original program would be unable to find the fiducial in this case and provide the measurements. But if you look on the right with the adjusted program, after making the changes, it can handle low contrast images. Okay. So during this process, I learned a lot. So there's obviously the technical component, like I had to learn how to do spreadsheet programming and sort of all the functions. So I started out by analyzing existing code, and I took notes on the different functions and cell dependencies and generated possible leads. That sort of helped me with finding the right parameters to adjust later on. And then also this internship taught me a lot about experimentation because there's only so much that the videos could explain. So I did try a lot of different tools and play around with the user interface and adjust the parameters from there. So it taught me a lot. This internship taught me a lot about being more open to experiment and try new things, which I found extremely helpful. And then also sort of balancing that with consulting the mentors in group, because there were a lot of team members who had a lot more experience and knowledge than me. So making sure to ask them questions when it was necessary was like instrumental in the learning process. So for example, when I was analyzing cell dependencies, that was extremely helpful. And it was actually Nick Pereira who introduced that to me. So shout out to Nick. And then sort of like in terms of the impact of my efforts, I finished like, I guess, the entirety of my project, and I sent like the new program and all the documentation necessary to implement this in other programs to Tauha, who's my mentor. So this should be able to be implemented if necessary. And then I just want to talk a little bit about the future of the field. Since automation is like the future of manufacturing, this internship was extremely helpful. Just because like I saw that sort of like the importance of automation, and also in like automating quality control in this internship, and like all those like fiducial circles you saw earlier are like microscopic. So obviously, you can't have people just checking every single one, because that'd be a bit slow. So then it really showed me like sort of like how like with mass standardization in production, control systems engineering and computer vision has like extremely bright future. Then from a computer vision standpoint, there's a lot of things you can do with image analysis. So in my internship, this is primarily in the context of manufacturing, but there's also applications in the medicine and automotive industries. And then as the primary like job in control systems engineering is being a controls engineer. And you work a lot with programmable logic controllers, robotics, and quality control. And the average salary is $67,261 per year, but that's higher with experience. And then in terms of where I'm headed, through this internship, I've learned a lot more about the practical application of advanced technology. I entered this internship wanting to be an entrepreneur or doing more startups, but larger corporate experience was also extremely fun, so I'm less sure. And if I want to start my own company, I found computer vision and automation extremely interesting, so I might consider entering that. It's also informed my decision on what I plan to study in college. So I was originally thinking something like CS and econ, but now I'm leaning towards computer engineering and operations just because I feel like I got a lot more interested in manufacturing and scaling and stuff like that, and then also the hardware component. Okay, and then with the last of my time, I just want to say a massive thank you to Tauha and Steve for providing me with all the mentorship and guidance I needed to succeed, and then the rest of the HP team as well. And then also a massive thanks to Saturday Academy and HP for providing me with this opportunity because I learned a lot. Okay, sorry, that was kind of fast. But are there any questions?
Great work, Aaron. You got it under time.
Yeah,
you
sorry.
sped up and you caught it. Good work.
Yeah.
Sorry.
Sorry.
Any questions for Aaron? I have a question for you. Is the work you did with the vision system able to be applied to other parts of the manufacturing process, or is yours just specific for year one checkpoint?
Yeah, so like I was working on, this is sort of like, I think can be applied a lot to other pre-inspection parts. But my mentor Tauha sort of assigned this to me just because like this system, like even though it had like a 90% pass rate, that's like a little bit like low, I guess, for HP. So like this was the primary area where they had that issue. But I think like because I had like the documentation and everything prepared, this can also be sort of like some of the learnings. If it can't like be directly copy pasted, it can sort of be like the parameter adjustments can still be used to handle low contrast images.
Great. Another question, what was the hardest part of your internship?
So for the hardest part for me was like, I guess it's kind of interesting because I talked sort of about learning about experimentation and then also consulting the team at HP and more knowledgeable team members. And for me, like the most difficult challenge was finding the balance because I generally like to try to do everything myself, I guess. So just because I feel like that's a really like cool way of learning, because then I feel like I'll remember it more. But throughout this internship, it was like sort of like still keeping some of that with like the personal like experimentation and trying new things, but also knowing when to ask team members for help, because they can really help accelerate that learning process and really guide you in the right direction, so that like you don't waste a lot of time. So finding the right balance between those was like something that was extremely difficult, but I feel like it's something I got a lot better at.
Right. And last question, did you eventually get used to the mummy suit?
Yeah, kind of. I went a couple times. I was still pretty slow at putting them on. My mentor Tauha was way better at them than me, and he always had to like wait to help me. But I got a little bit better. Maybe next time I'll get a little. I'd be a tiny bit faster than when I first started. But yeah.
Great work, Aaron. Thank you for sharing with us.
Thank you.
Okay. Next up, we have Michael.
Okay, let's see. Hello guys, can you hear me and see everything? Okay,
Ready.
great. All right, hello everyone. My name is Michael Gu, and I will be a senior at Crescent Valley High School. Today I will be presenting my work on skeleton-based deformations of objects. I have had the great honor of working with the professors and graduate students in the computer graphics department here at Oregon State University, and this presentation is the culmination of my work this summer, so I hope you enjoy. So today I will be talking about 5 main areas: the fundamentals of animation, skeletal structures as rigid as possible, applications, and future works. So animations are becoming more and more common in today's graphics-powered world. We see lots of uses for animations, most notably in the art and entertainment industries, but also in more scientific fields, such as in medicine for medical diagnostics, or in any field that requires data visualization. However, today we will be going back to the beginning, to the core basics that allow animations to be created, and it all starts at the mesh. A mesh is a subdivision of a continuous geometric space into a group of topological cells or shapes. Typically, a mesh is made up of triangles or quadrilaterals to simplify the rendering process, but it can be consisted of any polygon. A mesh makes up the surface area or skin of a 3D or 2D model. The vertices of the polygons that make up a mesh will become very important later, but for now, we can just take a look at the mesh over here created of a dragon and a group of children. And although it might not seem clear at first, its surface is actually made up of hundreds of smaller triangular cells. So skeletons are another crucial piece that goes into an animation. I will be going into this in further detail later, so for now, here's a brief overview. A skeleton is necessary in order for a deformation or movement or transformation to occur. Each bone in the skeletal structure controls a portion of the vertices of the mesh to a certain extent. And this is known as weighting, which is basically how eagerly a bone alters the positions of each vertex in the mesh. I created the skeletal structure of the dog in Blender, as shown here. And the process of creating the skeleton inside the model and setting controls for movement is known as rigging. So now that a model is properly rigged, we can deform the model by transforming the bones in the skeleton. The formal definition of a deformation is the action or process of changing in shape or distorting, especially through the application of pressure. In this case, we are not applying literal pressure to the model, but rather moving the bones, which changes the mesh's physical appearance. As you can see here, we have a yellow dot here, which is the control handle, and this is a large deformation of this dinosaur skeleton. So these 3 components allow us to make basic animations. One popular animation software is Blender. And Blender has long been a popular open source software for 3D rigging and animation. It is pretty intuitive and easy to use, and over the course of the summer, I learned how to do basic rigging and animation with Blender. This short GIF over here is just a piece of work I did with Blender in the short bit of time that I learned how to do some basic animation. So just like the skeleton of a human, the data structure of a code is crucial to how it functions. In relation to my project, I used hierarchical structures and linked lists to be able to write a program which can create skeletal structures for 2D mesh models. So now you might be wondering, why is data structure important to the skeletal system of a model? Well, just like our human bones, we require a hierarchical structure in order to move on a day-to-day basis. Intuitively, when we rotate our bones, we would expect that each bone below in its system would rotate in conjunction with the original one. For example, if we took the skeletal model here and there was no hierarchical system in place, if we rotated the femur, everything below it and its system would remain in the same place, which would obviously not be a very efficient way to move. So by implementing a hierarchical system, when we rotate one bone, everything below it and its structure rotates with it. So now let's go a little bit further into how the skeleton in creation and deformation program that I wrote works. Two functions that I created were the translate and rotate function. Oh, wait, linked list, sorry. The linked list allowed me to create the hierarchical system for my skeleton creating program. It is a linear data structure, which means that each element of the list is adjacent to one another. For the purpose of the skeleton, that means that each bone has a head and a tail. On the left is the code, which allows the hierarchical structure to exist. So basically this function add subnode is basically adding a node below it in the linked list. And if we look over here on the right, this is more of a visual representation. You have a head and a tail. And basically my add subnode function would add an element E below it on the list over here, and it would progress as you add more nodes. All right, now transformations. So the two functions that I created here are the translate and rotate functions. They are crucial to the deformation because they translate the newly created nodes to the correct position and can also be repurposed to transform the already created nodes in case they were improperly placed. They are also used to calculate the position of the deformed vertices. Since the 3D point nodes are being stored as 1x3 matrices or the XYZ values, we can create a translate or rotate matrix and do some basic matrix multiplication to calculate the transformed node positions. As you can kind of see here in the image, it's a 3x3 matrix for the transformation, which takes a dx and dy argument, which is basically the cursor position, and also a node argument, which is basically the selected node. And it's the same thing for the rotate, but with an angle value instead. Okay. So let's see. Oh wait, I need to go back. Okay. So as rigid as possible. So as the name suggests, as rigid as possible is a method for producing rigid deformations. Rigidity is basically a measure for how well the local surface detail is preserved. If local surface shape is not altered, there is no stretching or shearing of the mesh. As we can see with the before and after of the dog models shown over here, the local surface detail is not really preserved because as you can see in the neck region, the local surface area is slightly stretched. So now before I get into the math, I have to explain a few details. So the first is this triangle here, which I mentioned earlier, makes up the mesh. If we have a point J and a point I and a cell deformation from C to deformed C, if that deformation is rigid, there exists a rotation matrix R such that the edge length of the deformed edge length is equal to the rotation matrix times the original edge length. So oftentimes a cell deformation is not completely rigid, so we can estimate a rotation matrix using this energy equation below, which is basically the weighting of the edge length multiplied by the norm or magnitude of the deformed edge length minus the rotation matrix multiplied by the original edge length squared. Now, intuitively, if we think about this, if this first equation holds true, this value in the below equation would be equal to 0. So basically, the goal of as rigid as possible is to preserve the edge length and to minimize the energy or get it as close to 0 in order to maintain local surface detail. So now that I've explained most of the math behind as rigid as possible, it is now time to actually calculate the deformation positions. As rigid as possible uses a two-step method. It begins with an initial guess where base points are calculated from minimizing the energy variable that I mentioned earlier for the deformed set of positions. The second step is to calculate a rotation matrix that minimizes the energy, which causes the transformation to be more rigid. Since the rotation matrix that we calculated earlier will update all the positions to be more accurate, we can repeat this process until it becomes rigid or very close to rigid. And as we can see in this image here, the deformation becomes slowly more and more rigid, and it is clear that the model becomes less warped. So basically in this image, you can see here, it's kind of squished together in the center part, but as there's more and more iterations of the as rigid as possible technique, the curvature becomes more natural. Okay. So now that we've gone into the mathematics behind as rigid as possible and shown that it is effective, we must consider why does it matter or what makes it so special? So first off, as rigid as possible is robust. The technique guarantees equal or decreased energy in each iterative step. Prior methodologies did not consider this in their theory, or rather did not explicitly formulate an energy variable that they were trying to minimize. As rigid as possible was also able to run on a 2.16 gigahertz laptop with only 2 gigabytes of RAM, which means it can run on low processing power. And finally, it is easy to implement because the technique is very similar to its predecessor, the Laplacian method, which was already widely used. So here I have a short video, a demonstration of the skeleton creating program and the as rigid as possible deformation technique. So basically what I'm doing here is just with a few clicks of my mouse, I can create a skeletal system for this 2D mesh model here. And so basically creating the joint structure. And then by selecting a node, you can deform it rigidly. And as you can see here, the edge length is being preserved even as the model's shape is being changed. So basically, kind of like the basics of animation here. And this is just kind of a demo of how the as rigid as possible technique works. And that was it. Okay. So now future works. The future works of computer graphics is endless, but today I will be talking briefly about 2 areas of research. The first is skeletal extraction by mesh contraction. And as you can see in the image below, the mesh geometry's volume is slowly decreasing by contracting the mesh, as you can see here. And I will start hurrying up. And the second one is rig mesh, which is a method that allows the modeling and rigging processes to become one. Basically, manual rigging has always been very time consuming, and this work basically allows you to have automatic real-time rigging. So it's very effective. So in conclusion, I learned so much over the summer, and I'm so grateful to have had the opportunity to learn about computer graphics. I learned more about a new programming language, C++. I was introduced to the principles behind computer graphics, and I learned about new deformation techniques. I would like to thank Professors Yue Zhang and Eugene Zhang for organizing my summer internship curriculum. They were both super supportive and gave me many opportunities to interact with graduate students in the computer graphics department. And I would also like to thank my graduate mentor, Kevin Hung, for teaching me and providing me with resources over the course of the summer. He was a great guide and he always pushed me to learn more. And finally, I would like to thank the Saturday Academy, as well as my teacher monitor, Jennifer Henry, for keeping all of us interns on track this summer. This is a memorable opportunity that I will never forget, and I'm grateful to have been part of this program. And I am now open for any questions you might have. Thank you for listening.
Great work, Michael.
Barely scratched the time there.
That was great. All right, any questions for Michael? Did this internship change any future plans?
I mean, not really, because I was always interested in computer science as a field. And I think this internship really kind of confirmed what I already knew, which was that I wanted to go into computer science. And I think since computer graphics is like a more specific sub area, that's definitely something I'll be considering moving forward.
What aspect of computer graphics or application intrigues you the most?
So for me, I think just like the whole animation process in general. So over the course of my internship, I attended lots of like graduate reading groups, and basically they're presenting different areas of research. And it was kind of shocking, like how much research there is out there and how detailed this field can get with computer graphics. So like I learned about like surface light scattering, and basically when you're creating an animation, how to make it look as realistic as possible. And there's just so much research, and honestly, I was really kind of blown away. So
All right, any other questions? All right, great job, Michael, thank you.
thank you.
Next up is Jordan.
Can you guys see it?
Yes, we can see it.
Okay. Hello, my name is Jordan Kim, and I'm an intern working under Dr. Zhang for Oregon State University. Today, I'm going to be presenting on using interpolation and blending functions to create perfect splines. Oh, I'm so sorry. I forgot to share my video. I'm so sorry. So to start off, let me give a brief introduction to the field I'm studying. Throughout the summer, I've been working in the field of computer science. Specifically, my work deals with making computer graphics. The main subject I've been studying with this was Bezier curves and how to apply blending functions to make smooth arches. I used MATLAB for all the coding done throughout my work. MATLAB is really good at handling matrices. In fact, it's one of the defining features of the language that makes it stand out in comparison to other programming languages. When working with curves, I use matrices as data points. So naturally, a language that handles matrices well will be a perfect fit when working with curves. So first things first, what exactly is a Bezier curve anyway? Well, it's a curve defined by 3 or more control points, which are points that interact with the curve in some way. The actual curve only runs through the first and last control point in the set, while the middle ones define how the curve looks. On the left is a quadratic Bezier curve, which has 3 total points. The curve interpolates through P0 and P2, while P1 defines the curve. By the way, interpolation is when a curve goes through a point, like how the curve goes through P0 and P2. The formula for this is found above. A similar thing happens with a cubic Bezier curve, which is found on the right. The curve interpolates through P0 and P3, while P1 and P2 define the curve. The more control points, the more control you have over the shape of the Bezier curve. While they may seem the same, and sometimes even be used interchangeably, curves and splines are in fact different. A curve is made up of 2 endpoints and has a very basic design. Therefore, it cannot be modified easily. On the other hand, a spline is made of multiple curves attached to each other by the endpoints, forming a unique shape that a simple curve cannot create. It can also be modified a lot easier than a standard curve. Now that the differences between curves and splines has been specified, we can get to the class of C2 interpolating splines. The method described will allow us to create modifiable splines using interpolating and blending functions. First up is the blending function. The function takes 2 curves and creates a single line, as seen in the image in the right. If we plot maximum curvature of both curves and set an endpoint for one curve as the middle point for the other, we get an overlapping section, which is the gray area. Applying a blending function can get a smooth transition between the 2 curves. The formula can be seen here in the bottom, where theta from 0 to pi over 2 is a normalized parameter value. If we get rid of the overlapping area and only focus on the smooth transition, we get a single spline. You can create very intricate shapes once you apply the blending function across multiple different curves. For my study, I focused on Bezier curves. If you remember, quadratic Bezier curves are made up of 3 points, 2 endpoints and 1 point to define the curve. This point will be referred to as B1, while the endpoints are B0 and B2. B0 and B2 are easy to plot. They are just the endpoints. However, to get B1, we need to apply this equation in the middle right here, where t from 0 to 1 is the normalized parameter value for the Bezier curve at P. Although we can pick any point for t, it'll make things easier if we place it on the maximum curvature, where the peak of the curve is. As I explained before, this is used for the blending function. Solving for t in the cubic equation below should get us the point of maximum curvature. And with a combination of blending and interpolation functions, I was able to create shapes such as these. I merely had to pick the control points, and the program calculated the curves. The combination of blending and interpolation functions allows for versatility when making curves, so you can make complex shapes that couldn't be done with single curves. For the guitar image specifically, the numbers represent the order in which the points are generated. For interpolation functions, there are certain desirable properties that a curve could have. Desirable properties are ones that make it easier to modify and manipulate the curve. Things can get pretty out of hand easily if some of these aren't checked. The first one to look out for is avoiding self-intersections. As the name implies, it's pretty self-explanatory. You want to avoid the curve intersecting itself. And despite being pretty obvious, it's actually been a hard problem for many older studies to avoid. So when looking at interpolation functions, this is something to look out for. The next is being bounded. So to make sure the curve doesn't get too large, we need to set boundaries for how big the curve can get. This is called being bounded. If it's unbounded, there are no limitations to how big the curve can get, and it can easily go on for infinity, which would be undesirable. Next is local support. So local support means that moving one point in a curve will only affect the curve it's on, and the neighboring points will only affect the curve. This is the opposite of global support, which means that just moving one point will change the entire shape of the curve. And despite being self-explanatory, forming circles has actually been pretty challenging for some interpolation functions. So this is definitely something to look out for. Last but not least is curvature spikes. In some instances, the curvature maxima can deviate from the control points, which can cause unintended bumpiness and roughness in the shape. So although there are multiple types of interpolation functions, I'll just go over the one I studied the most, Bezier interpolation function. And this image on the left shows what kind of image you can draw. So first of all, there are no intersection curves whatsoever. And it's also bounded, which means that there's boundaries to how big the curve can get. It also has local support. So moving one point won't affect the entire curve, only the curve surrounding it. And as you can see in this image below right here, the curvature spikes are contained. The maximum curvature is seen in the purple area, while the shape of the curve is the thin green line in the middle. You can see that it's only self-contained around the control points and not somewhere like, for example, in between the control points. This means that the curvature spikes are contained. The only thing that the Bezier interpolation function has going against it is that it cannot make perfect circles, like you can see below in these two attempts for making circles. You can see in the right that adding more points will make it more circle-like, but this is impractical, and adding more points will only make things more complicated. You can also see it in the image where the eye of the elephant is sort of lopsided and almost oval-like, when in reality, it should be perfectly circular. Needless to say, there are many applications for this work in both production and consumer products. For example, Adobe Illustrator has a curvature tool that uses the math from the same paper I studied from to allow users to create accurate curves and shapes. In general, this work will help computer programs generate curves accurate to how we want, which can help computers be more adaptable when it comes to curves in the real world. It can also be used as a basis for 3D hair modeling. Hair is hard for us to make look realistic, especially because of its specific look and the way it moves. With accurate curves, it can help make hair that much more realistic. During this internship, I also created my own hair texture in Blender. How I did this is surprisingly simple. I started out by modeling a single hair strand. You can see from the image that I use Bezier curves to modify the way it bends. The points right here are the control points, and the hair strand acts as the curve itself. After creating a single hair strand, I just copied it and put it on a sphere, resembling a head. Modifying width and length can go a long way in making the hair look varied and natural. This method will produce hair in a cartoon art style and is not meant to be realistic. Just like how cartoons can make dramatized movements like that live action cannot. This cartoony hair can look appealing in certain circumstances where realistic hair doesn't. And thank you for listening. I'd like to thank Dr. Yu Zhang and Dr. Eugene Zhang for being my mentors and teaching me everything I know. I'd also like to thank Kevin Hung for assisting me throughout this entire internship. And without him, I wouldn't even be able to do this presentation. And I'd also like to thank Jennifer Henry for being my teacher monitor. And thank you to ASE and OSU for providing me with this opportunity. And here are the references.
Great work, Jordan. Thank you. All right, do we have any questions for Jordan? How long did it take to design the hair? How long did you spend on your hair product?
Around a week. It's surprisingly easy to modify the hair strands. So, and if you just copy and paste it, you can easily get varied hair.
Any other questions? All right. Thank you, Jordan.
Thank you.
Okay. We have a chance. Would we like to take a break? Or would we like to keep going? We're about halfway through. Walter, do you have any suggestions? Okay, let's take a quick break. We'll be back in like 5 minutes. So 11:05. All right, hopefully we are all back. Next up is Josh Bishop. I want to thank everyone for respecting the boundaries of not asking questions during, but saving your questions for afterwards. Some reminders. I will be giving a signal 2 minutes once you've got 2 minutes left and counting down until 12 minutes. We'll save time for about 3 minutes of questions afterwards. Okay. Not sure if anybody's back yet. This is the beauty of Zoom. But whenever Josh is ready, you can go ahead and screen share and we'll get going.
Hello, can you all hear me?
Yes.
All right, fantastic. 1 second. Okay. So, hello, I am Josh Bishop, as you heard. And yeah, this summer I was an intern for a research project at Oregon State University. Yeah, the project was funded by the National Science Foundation, and the main focus of it was to basically create a curriculum, excuse me, for middle school students to teach them computer science, but by using games to do that. Yes, you heard me right. I said games. Now, the first thing you might think of when I say that is something like, I don't know, titles like these, something a little familiar like that. That would be fantastic, wouldn't it? Unfortunately, I'm not talking about these. This is a little more modern than I'm talking about. What I'm talking about is something a little more traditional, more old school, like these games that everybody knows: tic-tac-toe, rock, paper, scissors, rolling dice. Now, before y'all get bored, let me explain. So why are we using these games to teach students? Well, there's a couple of reasons. One of them is that, well, it's a lot more accessible. It's more familiar. More people know tic-tac-toe than Half-Life Alyx, for example. And also, their simplicity lends well to explaining core fundamental computer science concepts that are being taught in this curriculum. For example, one of the things that is important in a game is the instructions for how to play the game. This is very similar, if not identical, to a term called an algorithm, which is basically just a set of steps for a computer or for anything really to reach a desired outcome. Another concept is, let's say, a game piece that you use, like that represents a player, or maybe scissors for rock, paper, scissors. This is an example of representation, which is very important when representing data in computer science. Let's hand gesture here. This represents scissors somehow. And another important concept is the how to win the game. For example, like with tic-tac-toe, you got to get 3 symbols in a row. This is the same as the objective that you're trying to reach, the problem you're trying to solve by using an algorithm. So yeah, those are the important concepts. With this curriculum, it's split into 2 different levels. The level 1 section covers those fundamental concepts that I spoke about, and doesn't even get into programming yet. They don't even touch that. This is because computer science is a little more general than just specifically programming. It's more about those like algorithms and solving problems, and programming happens to be a tool that's used in computer science. And also, it's a little more beginner friendly for the students because these are middle school students. The idea, if they're completely fresh to the entire field of computer science, if we suddenly bring in these big terms and these big scary language to learn, it's completely new to them. They may be scared away, so to say. But yeah, it's more beginner friendly for them. So that's level 1. Level 2, this is when the students actually start learning how to program using Boggle, or board game language. This is a custom language that was created for teaching students these computer science concepts. Yeah, they use this tool. Here, for example, we have a program written in Boggle that simulates flipping a coin. In this case, we tell, it's not entirely intuitive at first, but let's analyze it. Here we have, we're telling the computer that the coin side that landed, the side that landed up was heads. So then the computer tells us who wins based on that input of information. And in that case, if it's heads, Sam wins. If it's tails, Ollie wins. Another example we have here is it can actually simulate tic-tac-toe by drawing a board. In this case, we have, that's one of the data types that's actually used in Boggle, is custom type called board, because this is a board game language. In this case, you can input coordinates for the X's and O's to go to different spots on the board. Here we have an O in the middle and a X on the bottom left. Yeah, it's a pretty simple language, but it can be pretty powerful. So what did I do for this project? well, I did a couple of things. One of them was to go through the existing material and check for any mistakes or any ambiguities, anything that might be confusing to a middle schooler when they're being taught the material. Another one of the things that I did was to actually create some of this material. One of the things that I created was a worksheet and a lesson plan for students to learn about values or like numbers or like how they're used in an algorithm, for example, and how they can be more than just numbers. Another thing I helped with was actually participating with other OSU graduate and undergraduate students in Zoom breakout rooms for some student camps that were held at OSU this summer. These camps covered the 2 levels that I mentioned earlier, and each went about a week or so to cover the concepts in each level. Basically, my role in those camps was to help out the students with their assignments or worksheets if they were running into any difficulties, or explain any unfamiliar concepts that they were running into. This is where my relatively younger age came in handy, because a lot of the other research team members were on the older side, so having a sort of middleman to sort of be more familiar with how a middle schooler is thinking was really convenient, so that I can more easily see through the lens of one and understand why they were having troubles with an assignment, or identify problems that they might have before we even bring these assignments or worksheets to the students. So this was a really fun experience for me. All right. So what was my experience like for this? Well, other than the occasional, am I really up to this sort of task moments? I had a blast with it. It was really interesting participating in this. I learned so much about what goes into actually creating a curriculum or teaching students the computer science or programming, because I'm usually on the other end. I'm usually the student, but actually seeing what goes on and being on that sort of mentor sort of end was really interesting. And I actually learned a lot about what goes into it. Probably one of the most valuable things that I learned actually was when I was making those curriculum materials, because at first I was sort of agonizing over the details, but because those summer camps were coming up and we were actually going to be using the lesson plan and worksheets that I made in those student camps, there was a sort of time limit for that, so I had to get those done sooner rather than later. Instead of making them absolutely perfect the first time, the importance of iteration was crucial for this, so I could get first version out, get some suggestions, get the second version out, get more suggestions, more feedback. We even revised some of the worksheets completely. They were completely changed at some points. At one point, it was completely verbal. They were analyzing like written instructions, and at another point, they were analyzing cards for card games to determine different values. But the importance of iteration was crucial for that. So that's probably one of the biggest things I learned during that experience. The team was amazing for this. It was amazing. They helped make this experience amazing, which brings me to the thanks and acknowledgements. I would like to thank, of course, my mentor, Dr. Martin Erwig, for making this the best an internship it could have possibly been. And of course, my co-mentor, Aiden Nelson, he was an amazing friend throughout the entire process. And yeah, he was just a fun guy. And the entire Boggle team, it was amazing to work with. They were so welcoming. Even me, a new guy who came in at the middle of the entire project, they were extremely welcoming. Yeah, I would like to thank Jennifer Henry for being an amazing resource, especially when it came to making this presentation and the thank you letters. Yeah, I'd also like to thank my family, because funny story, my mom actually let me know that this was an opportunity 2 days before the deadline, and I had no idea I would actually get in. So huge thanks to everyone on the list and anybody I might have forgotten. I hope I didn't forget. And if you would like to find out more about the project, here are some links to their website and to the Boggle editor if you would like to actually try it out. And now I'll open up the floor to questions.
Thank you, Josh. That looked super cool. Is there a game mechanic you found particularly helpful in teaching computer science concepts?
Ooh, that's a good question. Let me think about that. Probably, probably game mechanics that had to do with like values, like I was talking about. Like, funnily enough, Pokemon cards were a good example, because they're so data heavy. There's so much information that goes into a Pokemon card. I don't know much about them, but a lot of the other team members did, so that was super helpful because they actually knew about it. But yeah, there was like HP or attack damage or defense that they had. It was, but also like different types of attacks or different actions that they could take. Having the different items or different players in the game really helped explain like data types or values to the students.
Very cool. Any other questions for Josh? Okay. All right, thank you.
All right, awesome.
I would like to request, I know that, we've been here for a while and half of us are already done, but please do not check out. Please give the same respect and that we gave the first half. Let's give engagement, respect, and attention on the back half as well. All right. So moving on, we have Anjana. Are you ready? Okay.
Yes, I am. Okay. So my name is Anjana. I'm a senior at Crescent Valley High School in Corvallis, and this summer I virtually worked at the Mixed Signals and Circuits Lab in the Electrical Engineering Department at OSU under the mentorship of Dr. Tejasvi Anand. And today my presentation is about transmitting and receiving data in a wired communication system. So you might be asking, what is a wired communication system? And it's also commonly known as wireline communication. And it's basically a system where data and information is transmitted over a physical channel, which is specifically a wire. Whereas if you looked at, in contrast, if you looked at wireless communication system, that would be, the channel would be through the air. And some examples are Ethernet cables, telephone networks, and some other ones are cable, TV. And in this picture, this is one of the PhD students' work, and you can see that copper wire through that board, and to the other board is a channel. So to start off, what I did, the most important things are the tools. And I used a software called Scopy which has many instruments such as the logic analyzer, which displays many signals, the voltmeter, which measures voltage, and programmable power supplies, as well as two very important ones that I'll be talking about later, which is a signal generator and oscilloscope. And then I used the ADLM 2000 active learning module by the company Analog Devices. And that is basically a tool that, that specializes in data acquisition, which is the process of making data digital. So using both of these together, I did my project. So the first step is creating data. So I decided to make a word into data, and specifically binary data, which is data that's either 0 or 1. And those just made, which are binary digits, are called bits. And I chose the word orange. And in Python, I wrote a small little code that converted orange into bits. So if there are 8 bits per letter, and there's a total of 48 bits. And then for this to be generated as signal, I need to save it as a CSV file, which is which separates each bit into commas. Instead of 0, 1, 1, it's 0, 1, 1. And then I imported that into Scopy. And now in the signal generator, you can see that this is the signal for orange, or at least the first part of it, because it's a very long signal because there's 48 bits. So each one of these is called a pulse, if you can see my mouse. And so this is that. And then next is the oscilloscope, which measures waveforms and displays the voltage signals. This allows signals to be observed by people, and it's a very important tool. And in this, it always keeps moving, so that's why it looks like it's in the middle of something. And if you notice there, it's a little on top, it's a little bit wavy instead of being straight like it was in the signal generator. And this is because of the high frequency. And now, like, let's say you want to convert this back into data, what you would do is you use a threshold. So a threshold is a level that determines the value of the sample. So in this case, we're using 0 and 1, so the threshold is 0.5. So like if you're into coding, this would be you can make a conditional statement and have anything over 0.5 is equal to 1, and anything below 0.5 is equal to 0. And you just keep doing this along the entire waveform until you get all the 48 bits that equal orange. But that's not very practical, even if it's a computer doing it. It's very slow, and this is just a word. Like, think about sentences, paragraphs, and all that. So that's where comes the concept of pulse amplitude modulation, which is also known as PAM. And the data is encoded in the amplitude, which is the height of the pulses. So this helps increase the data rate, which is the amount of data transmitted by the time. So a higher data rate, the faster it will be. So what I just showed you had a pulse amplitude modulation of 2. So there are 2 levels, which is 0 and 1. And this is all the symbols, and there's 48 symbols, and 1 symbol is 1 bit. So there were 48 bits in here. I'm saying 1 symbol is 1 bit. And this is what it looks in the oscilloscope. And then there's pulse amplitude modulation 4. So there's an encoder. So 0, 0 is equal to 0 volts, 0, 1 is 1 volt, 1, 0 is 2 volts, 1, 1 is equal to 3 volts. And it's like a key. So the first 2, you see 0, 1, and that'd be 1. And you would do that all the way through. And now from 48, it cuts in half to 24 symbols. So now that 1 symbol is worth 2 bits. So 2 bits are transmitted in the same time as 1 bit, which leads the data rate to double, which makes it faster, twice as fast. And if you look in the oscilloscope, now it looks very different. It looks more like steps rather than very weird steps, but it's not just 2 levels, it's 4 levels. So this is still not fully orange. This is probably the first 3 letters of orange. So to get that, we go on to pulse amplitude modulation, 8 levels. So it's 0 to 7, because you always start at 0. And this time you're taking 3 bits and converting that. So 0, 1, 1 is 3, and you keep doing that until you get this, and that's 16 symbols, which is a very small number compared to 48. And 1 symbol is 3 bits, and 3 bits are transmitted in the same time as 1 bit. So it's 3 times as fast as pulse amplitude modulation 2. So now if you look at the oscilloscope and you see this and count each of the pulses, there are 16 pulses. And if you remember, there are 16 symbols. So now you have the entire word orange in this one screenshot. And let's say you want to go back to the data, you would go and go use the encoder and also with thresholds. And this time you'd have more than 1 threshold, and you would find the encoding number and then convert that back into bits, and then you'd get the same bits to make orange. So yeah. And so now let's talk about the future of communications. Let's talk about of wireline communications. So this is a really big business. It's $1 billion business that will keep growing, and data rates become double as more people start to use it. And especially now during COVID, a lot more people are communicating, and so data centers are overloaded, and we'll always depend on communications, on whether it's wireless or wired. But specifically, wired communications will always be very important regardless of how advanced wireless communication is, because wireless communication depends on wired communications. For example, base stations, which would be like cell towers, communicate with other cell towers through actual wires and optical cables. And that's what makes it reliable. So I'd like to thank my mentor, Dr. Anand, the ACE program, Saturday Academy, and OSU. And any questions?
Nice work. What careers did you learn about that relates to the field, and what are you most interested in?
So one of the careers you learn about is electrical engineering, which is super broad. But even within that, there's something called an analog designer, who creates circuits that focus on signals and amplification. And other non-electrical engineering jobs are data communication technicians, who install, repair, and test communication lines. And I'm personally interested in electrical engineering because that can apply to any industry.
Yeah. What do you think was the most important lesson or thing you learned this summer?
I think this is it's really broad, but something I think that was so important was that I guess I never realized how much we depended on this type of technology. So that's really broad, but that's something that I think that was really interesting to learn.
Cool. Thank you. Great work. All right. Next up, we have Sofia. You ready?
Yeah. 1 second. Yes. Hi, I'm Sofia, and I'm a rising senior at Corvallis High School in Corvallis. And I'm going to talk a little bit about my project and this to bacteria. So Erwinia is a gram-negative bacteria that infects primarily apple and pear trees. It's a great concern for apple and pear producers because it can infect a whole orchard in a single growing season. This bacteria causes the disease fire blight that currently doesn't have a cure. So when an apple tree gets infected, they cut the branch, they burn it, and they hope it doesn't spread. This bacteria uses type 3 secretion system to infect plants. Pantoja is another bacteria, and it's also a gram-negative bacteria, but this one infects beets. It's the same family as Erwinia, but when a plant gets infected, it's treated with antibiotics. It also uses type 3 secretion system to infect plants. This is an infected beet. So what is type 3 secretion system? Type 3 secretion system is a protein attachment found in gram-negative bacteria, which is a type of bacteria that has a thinner membrane. Type 3 secretion system acts like a needle that injects bacteria directly into the cytoplasm of the cell. This allows the bacteria to manipulate the function of the cell. The signals that activate type 3 secretion system are unknown, but what is known are the master regulators, which are HARP-XY, HARP-S, and HARP-L. These master regulators have promoters, which code for or create this needle. As I mentioned earlier, the signals that activate type 3 secretion system are unknown. So my main questions were like what signal activates type 3 secretion system and how they do it. In order to identify the signals that induce type 3 secretion system, we built reporter systems that would allow us to test this bacteria under different conditions. In order to do that, we used GFP, which is a protein that glows green when it's activated. So we inserted this protein right after the promoter. So when it got activated, the bacteria would glow green. As a fun fact, GFP comes from jellyfish. So when this unknown type 3 secretion signal gets to the promoter, transcription starts and GFP gets activated and the bacteria glows green. But when there's no signal, when there's no promoter, GFP never gets activated and the bacteria doesn't glow. To build this reporter system, I did a series of steps. First, I did polymerase chain reaction, which is PCR, to amplify the promoter region of, Then I did ligation, where we inserted these PCR products into a vector with GFP. Then we use the ligation product to insert it into E. coli cells. And so that the cells would replicate themselves. This gives us colonies, which can be positive or negative colonies. Positive colonies have the ligation product in them, but negative colonies don't have it. In order to check whether the colonies had the insert, we did colony PCR, So the lighter the line, the farther it goes. So to check whether the colonies had the insert, we were looking, or we were hoping for products that were heavier than E. coli cells without the insert. After having a positive colony, we extracted the plasmid form of DNA, and we used it to transform the bacteria that we were working with. In this case, Erwinia and Pantoja. After this second transformation was done, the reported systems were ready to be used through a 96 well plate that goes into a plate reader for 24 hours that quantifies GFP signal. I set up my plate with 8 different types of sugar and the bacteria strains. As you can see in the picture, we need at least 3 columns with the same bacteria because mistakes can happen and machines aren't perfect. Having at least 3 columns with the same bacteria increases the accuracy of the results. After the plate being in a plate reader for 24 hours, we get this table that translates into different graphs. For example, in Erwinia, the sugar galactose was the most inducing one. So it's the one that made the bacteria glow like more green and brighter, while maltose was the least inducing one. Galactose is a really sweet type of sugar that is abundant in plants. This is a quick comparison of all the different types of sugar, and galactose is the gray line, and as you can see, is the highest one. Pantoja is different. Actually, fructose was the most inducing type of sugar, while dextrose was the least inducing type of sugar. This is a quick comparison of all the different types of sugar. And again, the line green is gray, is a fructose and is the highest one. So my key findings after this internship were that in Erwinia, galactose is the most inducing type of sugar, while maltose is the least inducing type of sugar. And in Pantoja, fructose was the most inducing type of sugar, while dextrose was the least inducing type of sugar. So the future. After building this reporter system, we could test these 2 bacteria under different conditions, in this case, under different types of sugar. So the next step would be to test this bacteria under conditions that are similar to the plants that they infect, until identifying the signals that induce type 3 secretion system and causes these bacteria to infect plants. So hopefully in the future, we can see some articles about these 2 bacteria. I want to thank Tauha Academy for organizing this internship, and everyone at the Anderson's lab at Oregon State University for giving me a great experience. Thank you.
Great work, Sofia. Nice job.
Thanks.
Any questions for Sofia? So is this kind of like antibiotics for plants?
It's first would be, this is kind of like first to identify what makes these bacteria infect plants, so we can prevent them in the future. Maybe antibiotics could be a solution for it. First step would be to identify what is causing this bacteria to infect plants.
What would you say was the most challenging thing about your internship?
Waiting, because a lot of these processes take hours. Some of them take about 2 days, and even with one of the promoters that I worked with, it took 3 days to get the result that we were waiting for to keep going. So I think waiting was the most challenging.
Yeah. All right. Thank you, Sophia. Nice work.
Thank you.
All right. And I believe we have one last one with Natalia.
Hi. So I'm gonna share it. Can you see it?
Yep.
Can you hear me? Okay. Sorry. Okay. Hi, everyone. My name is Natalia Pereria, and I'm a senior at Corvallis High School. Imagine a world without colors. It would be a boring world. Thanks to all the inorganic pigments, we have this fascinating, colorful world. The colorful chemistry behind each pigment is more fascinating. Today, I'll be using the Easton series of pigments as an example to show you how stunning it is. What is pigment? Pigment is a material that has a wavelength selective absorption. There are two factors in how we perceive pigments, which there are white light, which represents many wavelengths of energy when it hits a material, and some of this energy is absorbed, and the other one is reflected. And on the other side, we have blue light, which when a pigment that absorbs red and green light, but selectively reflects a blue light, will appear blue to our eyes. The differences between pigments and dyes is that pigments mean inorganic pigments and not organic dyes. Dyes are soluble in water and solvents, while pigments are generally insoluble. Dyes are generally less stable to light, heat, and chemicals as compared to pigments. New blue in 200 years. Here shows the history of the inorganic blue pigments. As you can see, before the discovery of OSU blue, the last new pigment was made 200 years ago. This is where everything starts, the famous blue paper and the famous blue man who made it happen. The discovery of the Indian blue in OSU or mass blue has attached attention worldwide as shown here and the worldwide press conference, such as the New York Times and the National Geographic. Origin of the blue color in yttrium indium manganese oxide solid solution. The pairing compound yttrium indium oxide is of white. The reason for the intense blue color of imine pigment is due to the addition of manganese. The crystal structure of imine blue is shown here. Both indium manganese occupy the same trigonal bipyramidal or TBP site, and the chromophore ion of manganese of 3+ has 4d electrons, as shown here. And as shown here. And these d electrons, they absorb light in the visible range to give the blue color. Amine series inorganic pigments. The discovery of amine blue has led to a research for another inorganic pigments with chromophore ions at the TVP coordination. So we replaced the indium ions in the nearly white indium in the yttrium indium oxide, which is right here. And this one is our pairing compound. So and then we replace the indium ions, and then we replace it with either titanium, copper, manganese, zinc, indium, yttrium, or iron, and then they compose green, orange, purple, or blue. How do we make and characterize pigments? Orange project. Optimize the orange color. Although I have made all the InMeme series pigments, I spend most of the time in the orange project. It is difficult to produce the bright orange color when making InMeme orange pigments. So during this project, we try to run some experiments and try to find the best composition and the best reaction condition to optimize the OSU orange color. Pigments preparation. Before starting, we need safety first, so the lab coat, gloves, and goggles. We calculate the correct amount of chemicals as starting materials and record it down in our notebooks. Then we measure our chemicals using a balance and put them together in the Moultons. In this orange project, for each synthesis temperature, I prepared a total of 4 samples with different amounts of iron. For each iron composition, 4 synthesis temperature were tested. So altogether, I had a total of 16 samples. So, oh my God. So here you can see all the notes together, the measurement, and my starting materials. Mixing and grinding. So now that all of our samples are ready, I grab a spatula and mix them together before the actual grinding. And after mixing them with the spatula, we start grinding. Good grinding and mixing will ensure good formation of target compounds and the following solid state reactions. Shake and bake. After grinding, we use the pellets press to make the pellets out of the ground powders. After we have our pellets, we go set up the furnace with the temperature and time we want, which were 1,290, 1,1300, 1,310, and 1,320. After heating, we let the furnace to cool down to room temperature. And then when our example is ready, usually the powder gets lighter than the pellet when we start grinding. Picking the best orange color. The final general step of making the pigments will be adding them to their sample vial. And to conclude with our experiment visually, the best orange color will be samples with a higher iron content combined with the synthesis temperature above 1,300. So you can see here, we have the different iron content and the temperatures that we use for them. Characterization of our pigments. X-ray diffraction detachments of InMeme series samples. Here we show the X-ray diffraction patterns of the InMeme series pigments with various colors. The X-rays interact with the atoms and the crystal structure. They give the diffraction peaks. As you can see, the patterns look similar, and that is because the InMeme pigments have a similar crystal structure. Introduction to the L star, A star, B star lab color space. One of the important characterization methods for pigment is color measurement. Here we introduce the LAB color space, which expresses the color as 3 numerical values, L star, A star, and B star. L represents the brightness, while the A goes towards green and red, and B goes towards yellow and blue. L star, A star, B star measurements for InMeme series. Here it shows the measure L star, A star, B star values for the InMeme series pigments. As you can see, the data points are where they're expected in the expected region to be. L star, A star, B star measurement for OSU orange samples. So based on the lab measurements for orange samples, we concluded that the best orange colors are associated with high iron content, and the synthesis temperature equals to or above 1,300 Celsius. And we use this little machine here to help us graph it. And here we have our best samples, but number 2 would be the best one. NIR and electromagnetic spectrum. In addition to color, another desired property of pigments is the ability to reflect heat. This is becoming especially important due to rising energy costs. Near infrared NIR is invisible light with a wavelength of 700 to 2,500 nanometers in the electromagnetic spectrum. So right there, this one is the one, is the heat that we can feel. Cool pigments and energy savings. Pigments that have a higher NIR reflexes are called cool pigments, and cool pigments can reduce surface heat buildup under the sunlight and lower energy costs. So you can see this building is attracting the heat and absorbing it, while this one is just let it go away. NIR spectra of the indium series cool pigments. All indium series pigments show excellent NIR reflection that is comparable to the commercial titanium dioxide. And our indium blue shows a much better NIR reflections than the commercial cobalt blue. So this one is the commercial cobalt blue, and this one is our mass blue. Summary reflection. So I learned more than I would have imagined. The world behind pigments is wide. Also, the community within the lab is so supportive, and all of them are awesome people. There's so many factors within it. Science explains so many things that surround us. And in this area, we're connecting art with science and making beautiful things out of it. Yes. So here I put an emoji of like before my internship with my knowledge with pigments, and this is my after. Acknowledgements. I want to thank the Saturday Academy, Maura Henry, Jennifer. Oh my gosh, I'm mistaken the names. I am so sorry. Okay, for this opportunity of being part of such a wonderful community. I want to thank Dr. Subramanian for giving me this opportunity to work in his lab with his research group. I want to thank Dr. Jun Lee, who helped me feel welcome, comfortable in a new environment, and for her guidance as a mentor, and for understanding me in every single aspect. I want to thank Yuan and everybody in Mass Research Group for helping me and for being super supportive towards me. And I want to thank the OSU for providing the lab facilities and the NSF for funding support. And here is my group. Yes, thank you.
Great work, Natalia. Thank you. Any questions? That was really good.
Thank you.
All right. So I don't see any questions popping in. Let's see. What was your favorite part of the process that you enjoyed working on?
My favorite part was being in an environment that I was really comfortable with, and everybody was really nice with me. I feel like really happy of going in every single day.
Awesome. Very cool. All right. How long did each iteration of testing generally go?
So you mean after we put the sample in the furnace?
How long did it take you to do like one round of testing?
Well, maybe with cleaning included, around 4 hours. And then after the furnace, I'll wait like 12 hours and then like maybe 1 more hour for it to cool down.
Nice.
Yes.
And how many rounds of testing did you do?
I did 4 because with 4 different temperatures. So the total of samples that I ended up with were 16.
Okay. Thank you.
Thank you.
All right, great work, everyone. We finished super early. We're very efficient. Thanks for sticking around, asking great questions, and thank you for putting so much hard work into these presentations. You all did amazing, and you should feel really proud of what you've accomplished. So thanks, and enjoy your afternoon. Bye, everyone.